The next half of section 10.6 talks about conditional convergence. So, a series that converges if the series of A sub n converge, but not absolutely. That means the series of the absolute value diverge is called conditionally convergent. So two things must happen. It turns out if you do this, then you still have to do this. But if I started with this first, if this converge, I'm done, because it's absolutely convergent. There's no way it could be conditionally convergent. And if this diverge, then I could go and do this, and that turns out to be the least amount of work. If I use the ratio test or the root test, recall, the ratio test will say that the original is absolutely convergent, which means it's right there, or it says the original is divergent, which means you're done. So if the ratio or root test apply, then pretty much you're done with the problem. And we know when that applies. That applies when you have an exponential or a factorial. So ratio test and root test will yield a result. You only do one. Otherwise, you're going to have to do two different tests. You have to show that the actual series converge and the absolute value diverge. So I suggest you start first with the absolute value, but it's up to you. So if I'm looking at the next set of problems, it says 15 through 48. Which of the series in 15 through 48 converge absolutely, which converge, and which diverge? So they're asking pretty much which of those is absolutely convergent. If it's absolutely convergent, you're done. Which converge? If it converge, then you check the absolute value and see if that diverge, and that's conditionally convergent. On your test, it's going to specifically ask which of those is absolutely convergent, conditionally convergent, or divergent. So I start with number 16. If I would start with the absolute value first, if I look at the series n equal 1 to infinity of 0.1 to the n over n, well, I do notice that this has an exponential in it. No need to really take that route. I could use the ratio test. Since it has an exponential, I'm in good shape because I already know that I'm going to get a result. And instead of dividing, I'm going to multiply by the reciprocal. Now, in the absolute value, the negative is going to disappear, right? So this is going to, plus 1. This is going to be negative 1 to the n times negative 1 to the n plus 1. I want to match the denominator so I could cancel a negative 1 to the 1, 0.1 to the n, 0.1 to the 1 times n, over negative 1 to the n, 0.1 to the n plus 1 times n plus 1. Now, this and that cancel out. Okay, I'm messing up big time. Let me rewrite that part. That is negative 1 to the n plus 1. Why did I write that? Oh, yeah. Times 0.1 to the n. So those two cancel out, that's right. This cancels with this. And I'm left with a negative 1 times 0.1 times n over n plus 1. If I divide by the highest power term of the denominator, something I should practice on doing, 0.1 is 1 over 10. You could leave it as 0.1. You could write it that way. That's 1 over 1 plus 1 over n. That will equal a 0.1, which is less than 1. The conclusion is that, therefore, the series is absolutely convergent. Again, if the series is absolutely convergent, I'm done. the only way a series could be conditionally convergent if the absolute value converge, if the absolute value diverge, which means it's not absolutely, but the original converge. If I look at the next problem, I'm glancing at this again. I could do this a couple of ways. It's best to start with this, because if the absolute value converge, then it's absolutely convergent and I'm done. If I apply the absolute value on this, this will be the series n equal 1 to infinity of 1 over 1 plus radical n. And let's see how this works. If I take the square root of n plus 1 and radical n, obviously this is bigger. If I put 1 over, this switches. But that right there is n to the 1/2, which diverges, so that's useless. The comparison test wouldn't work. So what I'll go for, what dominates the top, a 1, what dominates the bottom, radical n. This is a p-series less than 1, therefore this diverge. And if I take the limit, as n approaches infinity of 1 over 1 plus radical n, instead of dividing, I multiply by the reciprocal. I'll get the limit as n approaches infinity of 1 over radical n plus 1. That's a 0. I'll get 1, which is bigger than 0. Therefore, they both diverge by limit comparison test. So here I've just shown that the absolute value diverge, which means this series is, this is in parentheses, it's not absolutely convergent. That's not enough. Now I have to go in and say, okay, well, let's look at the series itself. So maybe I should put this on the right. Here we go. So here we've just shown that this series is not absolutely convergent. Now, if I look at the original series, I'll look at this part and I'll say, hey, that's positive, decreasing. The limit as n approaches infinity of 1 over 1 plus radical n equal to 0. Therefore, converge by alternating series test. So here I've just shown that the original converge and the absolute value diverge. What's my conclusion? Once I show those two, therefore, the series is conditionally convergent. And you could say conditionally convergent if you've shown that the original converge and the absolute value diverge. That's the only way you could have conditional convergence. Looking at number 20, I notice there's a factorial and an exponential. I don't have to worry about conditional because I know that the ratio test will do the trick. Negative 1 to the n plus 1 times negative 1 times n plus 1. Okay, I did that a lot. N factorial, n plus 1 times n factorial times 2 to the n over negative 1 to the n plus 1 times 2 to the n times 2 to the 1 times n factorial. So the factorials cancel out, the exponential cancel out, the alternating part cancel out. I'm left with the limit as n approaches infinity. The top has a negative n plus 1 divided by 2. That limit is infinity, which is bigger than 1. Therefore, the original series, the original negative 1 to the n plus 1 n factorial over 2 to the n diverge by the ratio test. And again, the only way you could have absolutely convergent if the original converge. Here I've shown that the original diverge. So if the ratio test applies, pretty much I'm done. And when would the ratio test apply? When you see a factorial or an exponential. Looking at this problem, if I take the limit as n approaches infinity of 10 raised to the 1 over n, as n approaches infinity, this will approach 0. That will be 10 to the 0, which is 1, which means it's attached to a negative 1 plus n, negative 1 to the n plus 1, which means this limit does not exist, i.e. it doesn't equal 0. Therefore, the original series diverge by test for divergence. And again, if the original series diverge, automatically it can be conditionally convergent. Conditionally convergent indicates that the actual series itself converge and the series of the absolute value diverge. If the original diverge, I'm done. It can be conditionally convergent. And if it's absolutely convergent, I'm done. The only way it could be conditionally convergent if both of these cases are satisfied, and that's not this case. If I look at problem number 36, a bit off, because if I pay attention, n equal 1, that is a negative 1 cosine of pi. N equal 2, I'll get a 1. So this is really the series n equal 1 to infinity of negative 1 to the n over n. Well, if I apply the absolute value, so if I look at, here, let me put it up there. If I look at the absolute value, series n equal 1 to infinity of absolute value of negative 1 to the n over n, that is really the series n equal 1 to infinity of 1 over n. This is a p-series, p equal 1, therefore diverge. So here, this series is not absolutely convergent. Now what? I still have to go in and say 1 over n is positive, it's decreasing, and the limit as n approaches infinity of 1 over n equals 0, therefore converge by alternating series test. And since I've shown that the original series is convergent and the absolute value diverge, I can conclude that it's conditionally convergent. Looking at number 32, I have two options here. I could say this is the series n equal 1 to infinity of 1 over negative 5 to the n. Right? So I could say in this case, I could say, well, that is the same as the series n equal 1 to infinity, negative 1 to the n over 5 to the n, right? Because that's going to be 1 over negative 5. The next term will be 1 over negative 5 squared, which is positive, then negative, then positive. Well, if I put an absolute value on it, if I look at the series of the absolute value of negative 1 to the n over 5 to the n, isn't that the series of 1 over 5 to the n? And wouldn't you say this is geometric? R equal 1 over 5 less than 1. Therefore, it converge. And since I put an absolute value on it, then my conclusion is that this series is absolutely convergent. So on your test, I'm going to ask, is this series absolutely convergent, divergent, or conditionally convergent? Of course, you could use the ratio test if you wish, but I thought this would be faster because this is geometric. Now, just a note, a quick note. If I was to look at this and say, look, this is the series n equal 1 to infinity of negative 1 over 5 to the n. Alright, the reciprocal that will change that from negative to positive. If I am to say this is geometric, r equal negative 1 over 5 less than 1, therefore it converge. I didn't put an absolute value on it. So I still have to check with the absolute value. That's why I always start with the absolute value first. That will be wise. And the homework is page 622, 15 through 39 odd. And that concludes this section.